All right, in our final review lesson for the unit, we're going to be taking a look at function notation and Desmos. Now, I put this one last because review may be the incorrect word to use depending on who your teacher was or what course you took most recently. So you may not have actually seen function notation before, and you may have never used Desmos, which is just an online graphing calculator essentially. But it's going to be a tool that we use regularly throughout the course, and we do a lot of functions through the course. In fact, half our units are on functions, so it's important to understand what they are. They tend not to be very complicated. You've actually worked with functions since grade 9 at least. You just maybe didn't call them functions. So we have to be a little bit more specific about what we mean by a function. So there's a little diagram here on the right-hand side that basically shows what a function is. And a function is really just an instruction. So it's an instruction. And what it does is it tells us what to do with an input. So it says, give me a number and I'll tell you what to do with that number. So it really is, I don't know why that end looks so funny, but it does. So it says, give me a number, I'll do the instruction on that number, and then I'll pop out what that instruction gives you. So in our little example over here, the input is a 3 and the function is x squared. So it says, you give me an input, I'll square it and tell you what the answer is. So you give it a 3, it says, okay, I'll square that. It gives you a 9 back. And you can see that if I plugged in a 5 there, it would give you a 25 back. And if I gave you a 7 there, it would give you a 49 back, and so on. So it's just an instruction that tells you what to do with an input. The thing that most students find confusing about this is the notation. It's not actually that hard. Unfortunately, it looks like something else. So for instance, we often write it like this. And that is not f times x, despite the fact that up until this point in your lives, you probably would have been taught that you've got a variable and then another thing in a bracket, so you multiply them together. This is a new notation that just says f at x is a function that tells me what to do with x. And it's often read as f at x. So x is the input, f is the function that's acting on that input. Now, in grade 9, you would have done equations like, for instance, y equals 3x plus 2. Y was a function, it just didn't use function notation. So we could say that this is a function of x, and that it takes 3x and adds 2 to it. So it's just telling me the input is x, and the output is 3 times that plus 2. That's all a function is. Now you'll see why the notation actually helps us when we get to Desmos, but for now, we'll just kind of leave it at that. We're going to replace our old y equals with f at x equals. And we have lots of other functions. And I should point out that there are functions that are of multiple variables. So for instance, the area of a rectangle is length times width. So area is actually a function of both length and width. I needed the length and width inputs in order to get the output area. So a lot of what we're going to be doing in this course is taking a look at numbers or graphs and trying to figure out what the equation is for them. And all we have to do is figure out what the pattern is in what we see. So I've got a few things here. I've given them different variables just for the heck of it to show you that it doesn't really matter what letters we use, although in many cases there are kind of some standard letters. But I want you to just take a second, and I'm going to explain these 4 table of values and their things first, but I just want you to pause the video for 1 second and take a look at them and see if you can figure out what the function instruction is to determine the output. So for instance, on the first one, I input a 1, I get out a 3. Well, there's a whole lot of things that could do that. I put in a 2, I get out a 4. I put in a 3, I get out a 5. I put in a 4, I get out a 6. Take a second and see if you can figure out what the instruction is, what the function is that tells the input what to do to get the output. So pause the video and try that for these 4. And when you're done, come back and I will explain and we'll make sure we're on the right track. Okay, I'm going to continue, assuming that you paused and tried these, knowing that most of you didn't, but that's okay. We'll get through this together. When I look at those inputs and outputs for x and f add x, I notice that the output is always just 2 bigger than the input. I input 3, I get 2 bigger, that's 5. I input 4, I get 2 bigger, that's 6. So what that tells me is my output function, given my input of x, is just equal to my input plus 2. Okay, if you didn't pause the video before, do that now for the next 3, now that you've kind of seen one, and we'll keep going. All right, we'll keep going if you didn't pause the video. The second one, can we figure out what the instruction is? Now here I've used an input letter of N and an output letter of C. It doesn't really matter, but what we want is our output C given our input of N. And what's the relationship between those two? Well, I could say my output, I put in a 1 and get out a 5, it's 4 bigger, but that doesn't work for 2. If I was 4 bigger, I would get a 6. But it looks like it's 5 times the input. 5 times 1 is 5, 5 times 2 is 10, 5 times 3 is 15, 5 times 4 is 20. So it's just 5 times whatever the input is. So that's my function. C at n equals 5 times n. Now the third one, this is one that we kind of already just saw. When I put in a 1, I get out a 1. So it could just be nothing. It could just be you put in t, you get out t. But when I put in 2, I get out 4. Well, it could be double it then. Not that that works for the first one. This third one triples, and the fourth one could... Wait, they're all squares of the input. So I can say that the output D at the input T is equal to the input squared. Okay, that wasn't too bad. Now the last one. What's the pattern here? I'm going to let you play with that one for a second, but I won't let you spend too long on it. If you're having trouble seeing it, it's double the input plus 1. So double 1 plus 1 is 3, double 2 plus 1 is 5, double 3 is 6, plus 1 is 7, double 4 plus 1 is 9. So this one says that the output, given the input, is just equal to double the input plus 1. Okay, and as far as these different variables go, the first one is generic function notation, which we usually use f at x. And if we need more variables, we tend to go g and h, and just kind of in order. C at n, that might be a function that gives you the cost depending on the number of items you buy. So these might be $5 items. Maybe you're buying t-shirts that are on sale for $5 each. The number of t-shirts you buy times 5 is the cost. The third one, d at t, this one was meant to be a distance at a time. So maybe this is for a falling object. The distance it's traveled is equal to t squared. It accelerates downwards. And the last one, b at a, is just completely generic, and I could have reversed the order of the b and the a if I wanted to, as long as I define what the input and outputs are. So now what we can do is evaluate these functions at different values. Now again, you did this in grade 9, except you used stuff like y equals, well, the first one we would use y equals x plus 2. And then the teacher might have said, what is y when x is 15? And you would say, well, y is 15 plus 2 is 17. Well, here we just use the notation and say f at x equals x plus 2, which means that f when the input is 15 is 15 plus 2, which is 17. So that's our new notation. Instead of saying f at x, which is our general thing, it's always true, we can find out the function when we plug in 15. And likewise, we got our t-shirts here, or whatever this actually is, and we could say, what is our cost when we get 8 t-shirts? And the answer is 5 times 8, because the input here goes there. So the input there goes there. And that would be $40 for 5 shirts. This one says the distance after 10 seconds is 10 squared, which is 100. And this one just says the value of b when I plug in 100 is 2 times 100 plus 1. And that's all there is to this function notation. It looks a little funny because it looks like multiplication, but it's not. it always appears as a variable at something or a variable times a bracket with something in it. All right, now what we're going to do is just take a look over at Desmos, and I'll be flipping back and forth just a little bit between things here. But we're going to go over and we're going to enter in the function 2x plus 5, and we're going to see what that looks like. So I am going to switch over to Desmos here, or more specifically, I'm just switching over to a Google window, and I'm going to go to desmos.com, if I spell it correctly. Desmos.com, and hit enter, and it goes there. And you should see this beautiful web page, and we want to open the graphing calculator. And it looks like this. Okay, so now I'm just going to go back quickly. We want to plug in y equals 2x plus 5. So up here, I'm going to just try and do that, make it as large as possible so it's clear. Y equals 2x plus 5. Just type it in exactly as you'd expect it to, and you get a graph that looks like this. So I can grab that graph, basically click and hold and drag or zoom. Oh, try that again. Where did my mouse go? There's my mouse. Okay. I can zoom in and out with my roller on my mouse. I can just click and drag around, but either way, my graph looks a little bit like this one. And what it says is when x is 0, 2 times 0 plus 5 is 5. When x is 1, 2 times 1 plus 5 should be 7. And 2 times 2 plus 5 should be 9. 2 times 3 is, yeah, there we go, 311, and so on. So it's going to give me all those numbers. Now you'll notice that this one's stuck. The rest of them don't. And that's because Desmos knows that intersections are important things, and that happens to be the y-intercept. So then the next part is, what does the 2 and the 5 do in that equation? So you might remember this back from grade 9. The 2 in the equation gave us the slope, or the rate of change. Which is a fancy way of saying every time my x value gets bigger by 1, my y value gets bigger by 2. Add 1 to x, add 2 to y. The 5 in the equation was the y-intercept. It's a starting value. So it's the value of y when x is 0. Now, I'm going to go back and just change the function notation, or the notation that we used in grade 9, to function notation. And all it does is replace the y here with f bracket x, and it knows exactly what to do. And you'll notice the graph didn't change. It's exactly the same looking as it was before. All we've done is we've changed from our old notation to our new notation, but the meaning is the same. All right, the nice thing about this is that if I want to figure out the value of y when x is 26.317, 26.317. I can do this. X is 20. Oh, geez, I got to try and find it over here. 26.3. I try and get it. Come on. Don't be a jerk. There. Okay, 0.31. I can't quite get it exactly there, but it's around 57-ish, 58. But what I can do is just ask Desmos to evaluate. Just got to double check that number. 23.617. 26.317. 26.317. So I've asked Desmos what the function evaluated at x equals 26.317 is, and it tells me it's 57.634. So that's the nice thing about function notation, is once I've defined what the function is with the f at x equals 2x plus 5, I can just say, well, what is the function when x is 26.317, or whatever other number I want, and it evaluates it for me. So I will say that you are allowed to do this on tests if you want to figure out what stuff is, instead of manually using 2 times 26.317 with your calculator. If you understand this and you're comfortable using it, you're welcome to. This is just essentially a calculator telling you double the value and add 5. And honestly, taking your calculator out and hitting 26.317 times 2 and adding 5 is pretty easy. But if the function gets really nasty, there's 10 terms in it. There's x squareds and x root x's and sine x's and everything else in there. It could be really tedious to evaluate with a calculator, but it's really simple to evaluate it using Desmos and the function notation. All right, switching back over. We can do all kinds of functions here, and I'll let you just take a few minutes. I would recommend maybe pausing the video, taking a look at these, and just punching them in on your own. I'm not going to bother doing that just as a time saver, but I will point out that there are a few things that you should know about the punching things in. First, if you're really stuck and you can't remember, I'll show you that Desmos has a little keyboard down here. So you can bring that keyboard up. There we are. And so if you need to do something like an exponent, you can put an exponent in there, or a square root sign, or, oh, look, there's more functions over here that it does, sine and cos and tan and a whole bunch of other things. Desmos does lots and lots of stuff. But if you forget, you can always use that. But for most of the stuff we do, we're going to just use a couple of shortcut keys on the keyboard. So here's a couple different types you can get. And I'd like you to just, when you're done the video, go over and try these all, or if you want to pause and do them now, make sure you're getting them. To see the different shapes that you can get for the different types of functions. And we'll cover several of these throughout the course. So we'll do quadratics, cubics, quartics. We won't do reciprocals, but they're interesting to look at because they're a neat shape graph. Square roots we don't really do much with. Exponential we'll do lots with. Logarithmic we won't do a lot with the graphs, but we will do a lot of logarithmic questions, and trig will be doing both graphs and questions. So these are worth looking at. I'll just point out that there's a few things that you should know how to type here. If you want to put an exponent in, just use the little up arrow on your keyboard. So enter in like x up arrow 2 and it'll automatically put the square in. Incidentally, if the exponent has to be something like x plus 3, you may have to put it in a bracket. Otherwise, it'll do like something to the x and then separately do plus 3. But you'll see that when we get to it. If you want it to do square roots, you could just type in SQRT, and as soon as you hit the T, it will automatically shift it to a square root. And for logarithms, I wouldn't worry about this now, but if you do want it to do logarithms and you need the little subscript of the 2, so basically the little 2 down there, you can type in shift and minus and it'll put you into subscript mode. Other than that, I think everything else is pretty straightforward. All right, I am going to talk about Desmos settings and looking at important key features and stuff like that. But let's actually just go over to Desmos now and do that. Okay, so I'm going to put in something maybe a little bit more interesting. Get rid of that for a second. I'll take a look at a quadratic, and we'll do x squared minus 3x minus 5. And you'll notice that I can see it. I already did some zooming in. Oh, by the way, if you ever want to go back to home base, just click on the home button there, and it'll kind of give you the default view. And it shows, if I click on the graph here, you'll notice that little gray dots show up in certain places. So there's one there, and one there, and one there, and one there. I think those are the only 4. But those gray dots represent important things about the graph. So for instance, the top 2, the ones that are on the x-axis, represent the x-intercepts. They show you what the x-intercepts are, the values when y is 0. This one down here, 0, -5, shows you what the y-intercept is. It tells you what value y you get when x is 0. And then down here at the bottom, we get 1.5 and -7.25. That's giving me a local minimum. So it's showing me basically where the minimum of that parabola is. And all those key features will show up on these graphs as little gray dots, and if you click on the gray dots, the numbers come up and stay. So that's just something you should know. Now, there is a setting thing up here, the little wrench that you can use, and I'm going to give you an example of why you might want to use it. So I'm going to do a weird function. Just bear with me. I'm going to do 10 times x plus 2 times x plus 1 times x minus 1. Actually, you know what? I'm going to change that to an x minus 3. And what you'll notice, just move this over so you can see the whole thing at once. 10 times x plus 2 times x plus 1 times x minus 3. By the way, I chose this because I kind of know what I'm looking for here. And you'll notice the graph is confusing because it looks like it's just kind of like 3 separate lines. We've got 3 points here. This is going to come into play for us soon enough, but you'll notice the 3 x-intercepts are minus 2, minus 1, and 3. Well, that's the opposite of the plus 2, plus 1, minus 3. Maybe that'll matter later. Okay, but either way, I'm having a hard time really seeing what this graph truly looks like. So I can zoom out a little bit until I can see all the important stuff on it. Ooh, that minimum there is going way down. Okay, there's the minimum way down here. So the minimum's way down there. Unfortunately, now that I can see the minimum and the maximum, by the way, I could click on them to get their exact values. Now that I can see them, the graph's almost just as confusing to look at. It's hard to really see what the shape of that graph is. So what I'm going to do is I'm going to go over here and I'm going to change some of my settings. One thing you can do if you wish, this first one just makes it more bold. It's called projector mode. It lets you see things better on the screen. I think, yeah, for the video, I'll turn it on. Sure, why not? What I want to do, though, is go back here and just say, okay, so this graph goes up and down really quickly, but all the good stuff happens between like -3 and +3. So what I'm going to do is just change my x scale. Instead of going from -76, I'm just going to go -4. I don't want to start it exactly on an important point, so I'll give it a little bit of extra room. And I think good stuff happens up until about 3, so I'm going to change this to 4. And now if I go back, not only can I see the minimum and maximum on my graph, I can see really what the shape of the graph looks like. I can see that there's a y-intercept there. There's an x-intercept here, here, and here. It's starting to get a little busy, so I'll turn those all off. But you can change the scale so that you can more clearly see what's going on with your graph. And you can do the same thing with the y's. Typically, when I'm looking at max and mins, I scroll in and out until I can see all the max and mins that are important. But then you can just play with the x's and say everything important happens between these two numbers. We don't have to worry about it now, but later on when we start doing graphing, we're going to have to go over and switch this to degrees. That's for trigonometry unit. We can skip that for now. And again, you can play with whatever one you want here. If you don't like these numbers, maybe you want to make this a little nicer. So you want to go from -150 up to, let's just do this up to +50. And take a look at what it looks like now. And you know what? Maybe I want this. This is like every other box is 1, but it's only showing it every 4th box. Maybe I want it to go up by 1s. So I'm going to change the x to go up by 1s. I don't like these minor grid lines. They seem to be in the way for me, so I'm going to turn them off. And maybe instead of going up and down by 50s along that axis, I'm going to change the y-axis to step by 20. Okay, and you know what? Maybe I'll do the x's by 0.5s. It looks like there's room. See, if I do something and it becomes too crowded, then it ignores me and says, no, I'm not doing it by 0.5s. I'll do it by 2.5. So I'm going to change that back to 1. Okay, so that let me change the scale of my graph a little bit. I think it looks just a little wee bit nicer. Okay, so that's basically it for the settings feature. You can play with it yourself and see what it looks like. There aren't too many other options I think we care about. If you're someone who likes darkness, you're a vampire, turn on the reverse contrast. You can see it that way, but usually I'll leave it there. And I think that's about it. Oh, one thing I do want to point out about functions, and this will become more obvious as we do more functions in the course, is that functions have a special property. And that's that all functions pass something called a vertical line test, which means if I give any vertical line x equals 3, or x equals 1, I guess, you'll notice it only passes the function in one point. And I can change this. I'm going to put a slider in here to make this. What just happened? Okay, never mind that one. I'll do -2. It only passes the function at one point. A property of a function is that it can only have a single output for any given input. It's an instruction to do on something. It can't yield more than one answer. So when you say double a number, it can't say, well, okay, then the number's either 7 or 15. There's only one answer to doubling something, and that's to double it. So outputs are always going to be only one possible option for a given input. One input has at most one output. It is possible to have 0 outputs. For instance, if I say I take the square root of numbers and you give me -3, I could say there is no square root of -3. So it could have no outputs, but it can't have more than one. That's the definition of a function. Just to give you an example of something that doesn't do that, here's a fancy little relation here. I'm going to just go back and change the steps of these. I'll go up by 2s, I guess. There we go. I could do a function, I could do an equation that looks like this. X squared plus y squared equals 25. And that gives me the equation or the graph of a circle. So a circle is a perfectly valid relationship between x and y, but it is not a function. And the reason for that is it fails the vertical line test. If I turn on x equals -2, you'll notice it goes through the circle there and there. So this is not a function. A single x equals -2, gives me 2 possible outputs. You know what? Let me make this a nicer one. I'm going to make it 3. If I input 3 for x, I get y equals 4 or -4. And as soon as I get multiple outputs for a single input, it's a relation, but it's no longer a function. And we're only going to really deal mostly with functions in this course. I thought I'd just point this out because the equation for a circle is pretty straightforward. It's x squared plus y squared equals radius squared. So if I want the radius to be 5, I put in 25. If I want the radius to only be 4, I would put in 16, and so on. But that's something to know about functions, is that they pass a vertical line test. A single input can at most have one output. All right. I think that's all I wanted to mention about those. What I'd like you to do is try some of these practice problems. Mostly it's just practicing using Desmos and understanding the notation. Shouldn't take you more than a couple minutes. I'll leave you with that, and that completes our review, and now we can jump into the actual real course. And we're going to start off with, well, maybe I'll keep it as a surprise. You'll find out in the first lesson. All right, we'll see you later.